For this week's lab, my group was tasked with measuring the force between two permanent magnets as a function of the separation between their center of mass. To demonstrate this, my group constructed a tubular test over a scale with varying masses weighted down on a repelled magnet. This allowed us to measure the repelling force of the magnets using the scale value and measure the distance between either magnet's mass using a ruler. Provided was two neodymium magnets and a plastic cylindrical tube, as well as a scale and retort stand with corresponding clamps. My group sourced a ruler and some weighted ball sinkers to use as the interval masses per measurement of downward mass acting on the magnets. The retort stand and clamps helped stabilize the plastic tube above the scale so the repelling magnets were aligned as best as possible. Magnets have two poles, referred to as north and south. Like poles repel each other, whilst opposing poles attract one another. Magnets are not divided into north and south monopoles, as magnets cannot have one pole and hence only dipole magnets exist. Like electric fields, the magnetic field quantifies the force a permanent magnet experiences due to the source of the field. The energy of a magnetic field around a magnet flows from either pole towards the opposite. Magnetization is the density of magnetic dipoles in a material. For this lab experiment, the demonstration of opposing magnetic poles is seen through the plastic tube and aligned in such a position that varying masses can be added to measure variance in the repelling magnetic force. To find the force between the magnets, the mass being produced by the weighted sinkers being applied on the top magnet was recorded and multiplied by gravity to find force in newtons. In order to do this, however, we first needed to individually weigh the magnets and the sinkers so we could measure the change in the values produced by the scale. Increased weight was applied onto the repelled floating magnet by dropping one sinker weight at a time. As the same poles of the magnets get closer, the repelling force between them increased. The whiteboard eraser, which was between the scale and the magnet, served as an insulator from the neodymium magnetic field disruption. However, it did not perfectly isolate the field as the scale results fluctuated when left to rest. This is an example of how magnetic waves, when accelerated, transform into electromagnetic waves and hence able to penetrate any medium and travel through the vacuum of space. The data collected is presented in tables relevant to the trial mass, distance, and force. All mass values recorded in grams were converted into kilograms in order to be in the correct units to apply the force formula F equals mass times acceleration, which due to gravity is 9.8 meters per second squared. And as for the distance, which was measured in centimeters, all values were also converted into meters for simplicity of analyzing the data on a graph. Each measurement was recorded into a new respective table in Excel and plotted on a graph. As the graph is decreasing exponential, the data is easier to view when it is closer to being linear. A second graph was then created to show the log force over the log distance to better illustrate the relationship of the distance between the neodymium magnet and the subsequent higher repulsion. As shown by the curve, as the distance between magnets decreases, the corresponding force increases as not only more mass is being applied, but more repulsive force is being pushed downward by the opposing end of the magnet into the scale. To better see the magnet's repulsiveness isolated from the increased mass, each value of mass per interval was subtracted by 8.4 grams as each sinker ball weighed this much. This allowed us to view the exact amount of change in mass as a result of the closer proximity of the repulsiveness from both magnets. As per the graph, it is obvious that when the distance between both magnets decreases, the intensity of the repulsiveness increases. Therefore, the margin of error during this experiment is due to the lack of consistent values being measured by the scale as the magnetic field of the strong magnets interfered with the instruments inside the scale. This is a reason why the results are not perfectly linear with or without the sinkers. The consistency of the repulsiveness behavior should remain constant, however, this is not the case. To minimize this error, a larger isolation of the magnetic field would be needed, or an alternative method to find the force using distance alone may be usable.